Awesome. Okay, so just as a little bit of background, this is part of a presentation that was given at the NESI conference a week ago, and I'm only one of 4 speakers that were on that session. There were other folks doing a great job. I can no way do justice to what they did, but I'm just going to present my piece of it as well as a little bit of an introduction. So it's a retrofit of a set of existing buildings. So this just shows an overview. This is Moran Square in Fitchburg, Massachusetts, one of those older mill towns. So it's an existing firehouse, mass masonry, as well as a commercial building just around the corner. You can see there's an empty lot between the two of them. The firehouse is down here. And the plan is to go ahead and renovate these 2 existing buildings, as well as to build a new construction building infilling between the 2 of them. There are a bunch of restrictions and project goals here that are in conflict and push-pull against each other. Number 1, passive house performance. Number 2, it is completely reliant on historic tax credits to make it work. So there's National Park Service weighing in, as well as there's a goal to use low carbon materials in this entire project. So the part of the presentation that I dealt with was specifically on the enclosure, the retrofit enclosure design for this project. So whenever I give a talk about mass masonry walls and insulation, I just want to make sure we're all talking about the same thing. So a mass wall is the classic foot-thick New England mill building solid masonry wall. The concept of how it works is that when it rains, moisture is safely absorbed in the material, stored there, and released later when things are drier. We can store that moisture in there without being damaged. So there's no actual drainage plane, waterproof layer. It's reliant on the mass of the masonry in order to work. So another thing I say whenever I give this kind of a talk, if you have an existing mass masonry building, the safest way to retrofit it is always on the exterior. It's both the safest in terms of durability and lowering condensation risk. It also has typically the best energy performance out of all the options. I'm just showing an example of an eaves overclad as well as a metal panel overclad on an existing building. The thing is, there are many historic buildings where that's just not really on the table. Like there's no way that I would do an eaves overclad of a beautiful old building like this. Historic preservation does have its role in that. So the problem is if we insulate on the interior, that runs us into potential durability risks. So what are the specific risks in cold climates? So what I have here is just a section of a masonry wall. What I'm showing here, indoor conditions, maybe 70, 20 degrees outside. And you can see that the temperature drop through the assembly is basically through the continuous layer of masonry. A solid layer of brick is not a great insulator. It's about R5, but hey, it's better than curtain wall, so that's saying something. In contrast, though, if we go ahead and insulate on the inside, you can see that insulation in here, we're doing most of our temperature drop through that insulation layer. That's why they sell insulation in the insulation aisle, and bricks are not in the insulation aisle because they're not very good insulators. So what's the result of that? One is that the majority of that wall in terms of temperature is running below freezing, while before only part of it was. And we've also cooled off the entire masonry surface. So let's go back into the potential risks. One is the potential risk of freeze-thaw, damage to the brick due to moisture and freezing. Another potential risk is air leakage condensation on the interior face of the masonry, which is going to be colder than it was before. In addition, there is rot and corrosion risks of the embedded elements like joists that are pocketed into that masonry wall, partially outside of the insulation. And just as a final point, anytime you're putting anything on the interior of a masonry wall, insulation or not, you're covering it up, which makes it harder to see when there are problems. For instance, if you have plaster or bare masonry, it's pretty obvious when moisture is getting through and you're bubbling off your plaster. Once you cover it up, a lot of those tells are going to be a lot less obvious. So getting into these in a little bit more detail. So the first of those risks was freeze-thaw. So that freeze-thaw damage occurs to brick When you get it really wet, we're talking drown it in a bucket kind of wet, and then you cycle it above and below the freezing point, or actually more specifically, all the way down to maybe 23 degrees. That type of cycling can result in damage like this, where the surface flakes off, kind of like phyllo dough. Basically, the whole surface comes off in a layer. You can see it's pretty obvious what was going on over here. Is this is a Boston building, downspout got disconnected for a while, was dumping a lot of the roof's water right on this brick wall. Presto, you have this kind of damage on the brick, that phyllo dough flakiness. Oh yeah, sorry, just a quick piece of housekeeping, by the way. Feel free to screenshot or whatever, but this entire slide deck will be posted on BSE's website, so you can grab it there. But getting back to this, so so the key thing about freeze thaw damage: insulated, uninsulated, heated, unheated, doesn't matter. It's all about, does the water get dumped on the brick? Another thing to realize, though, is that some brick is more or less freeze thaw resistant. There's good brick and there's bad brick. So this shows another Boston area building, same disconnected downspout, dumping like crazy. You can see that the mortar is completely gone. You could pluck the bricks out of it, but the brick surface, that looks pretty much fine. That's a very freeze thaw resistant brick. Now you can measure this specifically with something called the critical degree of saturation, or S-crit, but that's another half-hour talk in itself. Another thing to realize about freeze thaw is that climate matters. It's going to be the combination of where it gets cold and freezes and where it gets really wet. So for instance, we take a climate map, take the cold and very cold climates, combine that with where it actually rains. For instance, this light blue is where we're under 20 inches a year. And as a result, this red is basically the areas where you do have to worry about freeze thaw damage more substantially. Another potential risk is condensation on the interior side of the masonry wall. So this image shows the dumb old way that we used to insulate these kinds of walls, where we have a stud frame wall, a poly vapor barrier, and airspace just to make up for the waviness of the wall. So what happens? Interior air leaks through the poly where there are imperfections, condenses on the wall, cools down, and then forms this continuous convective loop, just letting more and more moisture build up there. To make this kind of a thing actually work, you need to be perfect, and that's not really happening. And also that air gap creates more of a chimney, makes that problem worse. And if anybody ever says, oh, that's like crazy building science, doesn't actually happen, your theoretical problems. This is a building that I investigated that was suffering that exact problem. Concrete warehouse in Philly. I could wipe the water off the back of that wall, with my hand. It was so bad coming down that it leaked through the floor, and the folks in the unit below were complaining about, hey, my window's leaking. I'm getting all this water through my window head. It's like that's how bad it was. Yet another question that I get whenever we talk about insulating mass masonry walls is, do we need to insulate them? These are, mass walls. The code says we don't need to insulate as much. Shouldn't it be fine on its own? So, what I did was just a really basic WUFI simulation, square meter of wall, measured the heat flux by month through it, starting off with uninsulated foot thick masonry R5. And, of course, WUFI accounts for solar gain, rain, thermal mass, all of those real world issues that you'd expect. And, obviously you can see heat flux is greater in the colder months going out. Heat flux is inward during the summer, exactly what you'd expect. This is a Vermont climate. Then I did the same wall, simulated it with 1.5 inches of close cell on the inside of the wall. Surprise, surprise. Yeah, about 60% reduction in heat flow. That's what happens when you add that much, you change the R value of the wall by that much. It's just a completely basic number. Bumping that up to 3 inches of spray foam, diminishing returns, you're cutting half again as much of that heat loss that's through the wall. So another of my colleagues did a set of simulations looking at mass versus no mass, high mass versus low mass insulated wall. It's net effect of about R1 in a cold climate. I'd say like, wait, doesn't, thermal mass does make sense. And that is absolutely true in climates where you have a diurnal variation, where the outdoor temperature is varying up and down, above and below the comfort condition, hot during the day, cold at night. Desert Southwest is the classic example. With that thermal mass, it takes that uncomfortable at both ends situation and basically damps it out to something closer to comfort conditions. In contrast, in New England, what do we got? In the middle of the winter, the temperature varies between cold and frickin' cold. So, damping out that signal is not going to help you very much. John Straub has very been instrumental in my building science education, and he often uses this example of the moisture balance, talking about potential risks and durability with assemblies. So you can think of an assembly having wetting going on from the outside, moisture sources, and simultaneously it's drying out. As long as drying is happening at the same rate as the wetting, you are not overwhelming this bucket, making it heavier than the safe storage capacity, and you're not going to knock over this teeter-totter. If you have too much wetting, exceeding drying, you might start to have durability concerns. So, when we insulate on the inside of this wall, we are decreasing drying. That evaporative energy flowing through the wall is being cut off because we're paying for it, and we want to reduce how much goes out. However, as a result, we have less drying ability of this assembly. So what we want to do whenever we do one of those retrofits is look at the wall and reduce or control wetting to compensate for this reduced drying. Okay, a whole lot of background so far. So let me just jump into a little bit more concrete stuff of the masonry wall assemblies. So this, in this spray foam assembly, for whatever its negatives, it's pretty tried and true, and it works very well. Spray foam does an excellent job of controlling airflow. It's, with minimal supervision of creating a decent air barrier, avoiding those condensation problems. It is moderately tolerant of moisture. So if you occasionally, once in a while, get water leaking through your wall, it can tolerate that without a problem. This shows it with a stud frame wall, metal stud free and clear of the foam, and an interior finish. That being said, that is definitely not actually is a little bit more background. Folks have been doing this in Montreal, a very cold climate, back to the 90s. Folks have been going back to look at this, and as far as anybody can tell, this is not a massive durability problem by any means. These buildings look fine. That being said, we can use other solutions. This shows an example of you take your masonry wall, put on a parge coat, a fluid applied air and water barrier just to control how much moisture gets through, pin on some mineral fiber, build your stud wall, interior finish. I'd probably use this only down up to climate zone 4, New York City. Going colder than that, you're getting a bit riskier. You could also do the same kind of assembly with a stud frame wall with cellulose, for instance, but once again, you are worried about the humidity control issues. The climate zone, and also humidity is also, interior humidity in winter will be critical to making this work. It might work fine at 30% humidity in winter. At 50% humidity, you might be running into problems. This would be a, building on that previous wall, putting on a interior smart vapor retarder, air and vapor control, building a service cavities to run your electrical so you're not punching your air control layer full of holes. That's a pretty darn good wall, but it's, there's a lot of moving parts in there. But then again, I'm talking to a passive house crowd, so that's probably, dirt simple. So what was the assembly that we came up with for the Moran Square project? Like I said, we have a bunch of push-pull requirements that we were fighting with. First of all, National Park Service, historic, told us we could only build in 4 inches from the original line of the plaster to avoid a thick build. But on top of that, for a passive house, we wanted airtightness and a high R value, kind of conflicting requirements. So the way we went about it was fluid applied air water barrier on the inside of the masonry, pinned a couple of inches of mineral fiber to the inside of that, and then a stud frame wall. Now, the ideal location in terms of an air barrier would be to put the air vapor control layer there in the middle of the wall. Unfortunately, we do need to insulate the stud frame cavity because we're trying to maximize how much R value we can get in a limited amount of space. So this is a bit of a push-pull that's still going on in the project. This is less than ideal hydrothermally, but the problem is Putting our air barrier on the interior is going to fill it with Swiss cheese holes of electrical boxes, T-walls, etc. Still being resolved. In addition, there are other parts of the building where historic restricted us to barely a 2-inch build-in, so we basically had to put our air vapor control directly behind the interior tongue and groove wainscoting finish. So moving on from that, just the basic walls, what were some of the tricky enclosure items that we were evaluating and looking at? So one key thing whenever we look at a masonry building for retrofits is what are the existing patterns of damage and or moisture accumulation? And what can we learn from that to try to prevent those mechanisms, keep them from happening? So the classic spots that we often look is what Joe calls where the building touches the ground and touches the sky. So the top of the building, the parapet, the top corners, those will get nailed by driving rain, the wind whipping it around the building, as well as those outside corners, as well as down at the base of the building, you have splashback. On top of that, you also have windows. Windows do not absorb any of the water that hits them, so that runs down and then drools onto the wall below. That's why you see these types of mustaching patterns down below most windows a lot of the time. It's often very useful to take a look at the parapet of the building. Number one, it's extremely exposed, and also it's going to be cold. It is not getting heat from the inside. Remember, it has a parapet is a fin that has outside on both sides. So that's going to be a very good tell on how does this brick behave without interior heat. On top of that, the best test of all is if this building has been mothballed and unheated for a bunch of years, they've been doing the perfect test for you of figuring out how will this building behave if we don't have interior heat flowing through the walls. Like, that's what we got. So what are some of the things I looked at when I was looking at these buildings? Overall, the brick was in relatively decent condition. One example of a problem, though, is if you look at this condition over here, you can see the surface is a little bit spalled. The mortar joints are kind of eroding at the back of the firehouse. So what is going on here is called capillary rise. So there's moisture in the ground or running off the parking lot. It is wicked up through the masonry and the brick, and it carries salt, dissolved salt in that water that's rising. It later evaporates out through the face of the brick, and when it evaporates, it leaves the salt behind, causing this type of erosion of the mortar joints and of the brick surface. You can also see something that looked kind of like that at the front of the building, but you don't see any damage over here. So my best guess is this is damage from 100 years of the oil tank guy banging his hose into the front of the building. In contrast, though, the Syndicate building, that commercial building next door, brick was pretty nice and intact. This damage over here was due to window runoff, but you walk further down the sidewalk, this granite curb is missing. And what's probably going on here is, once again, capillarity causing this type of brick erosion and damage. So one thing to realize is if you want to retrofit a detail, you see damage like this and want to retrofit it, I would pull out the surface layer of brick, put on some type of waterproofing, and then go back with a granite curb. Granite does not absorb water, so it doesn't have capillary damage, highly resistant to freeze thaw as well. Another spot we looked at are windows. So this shows on one side of the firehouse, and you can see very clearly that water has been running off the window, going over the sill, drooling onto the brick wall, eroding that brick underneath it. Just a classic tell. So what you want to do, a lot of old stone buildings have this great drip notch on the underside of the sill to break that surface tension and drip that water away, but we did not have it here. However, if historic lets you, you can retrofit this type of a detail, cut in a piece of metal with a sharp drip edge so that it kind of runs off and drips off before it hits the wall below. Another issue that we can see here is the roof. You see all this black staining coming off of the parapet. Man, what's going on there? Went up to the roof, and it's basically nothing is actually matching up with all of these stains. What I can basically guess is that there were previously coping stones leaking, causing these stains before this roof was retrofitted. Overall, the parapet looked pretty decent on the scale of things. Anytime you have a parapet situation, the more you can push out a drip edge, even just one 2x4's worth, the more you're protecting the wall below. Also, dumb stuff happens. Like over here at the back of the building, what probably was happening is that the saddle detail was flashed wrong, dumping a whole lot of water onto the brick wall below. So moving on to another topic, just in terms of the enclosure retrofit in general, we had the choice in these buildings of going with a vented or an unvented roof. So there's actually a small walkable or crawlable attic below this low slope roof membrane inside the parapet. So one of the options is let's build up foam on the outside, usual commercial roof, maybe supplement it with additional additional insulation in the roof rafters below. We have to insulate the wall though. That being said, that can work, but with the mechanical systems that we were using, there was not really any need to fill up this attic with mechanicals. So instead, what we decided on, can we just go with a vented attic where our air barrier is the fire ceiling is carefully sealed, including to the masonry wall, a thick layer of cellulose insulation, low carbon sequestering material, very cheap. You can go very, very thick with a catwalk above for inspection, and bake it into a vented outdoor space. One of the key tricky things though is making sure that you actually have outside airflow through this type of a low slope attic situation, which is often difficult given the lack of head height. So one way to go about it is you add a cupola. So we added a cupola on the front of the building, louvers at the back. That's about as, it's a compromise, but pretty reasonable on the scale of things. Another thing that you deal with when you are insulating a mass masonry building is potentially thermal bridging through situations like T-walls. So this shows the existing firehouse and commercial building, and the curved front is the new construction building being infilled between. So one of the problems are those T-wall situations that are created. If you do thermal analysis, you can see that that solid masonry party wall is basically wicking heat to the outside. Yep, it's a thermal bridge when you're only insulating on that exterior wall. That being said, a pretty reasonable approach to reduce that thermal bridge is you just continue your exterior wall assembly around the corner and basically run it around to try to insulate a little bit more of that T, and it does a pretty decent job of reducing how much heat flux is going through that condition. In addition, you can kind of turn your head 90 degrees and think of this another way. So this is a situation where the existing building, one of the masonry buildings, is hitting the new construction building. You can see it's conditioned space on the first floor, and the ground floor is a unconditioned parking garage. So you guys can probably see that we have a big masonry wall sticking down over here. That's going to be a thermal bridge pulling in cold from outside. So all that we can basically do is try to insulate that wing and try to reduce or control the degree of that thermal bridge. Another tricky situation we had to deal with is because that ground floor is a parking garage, the ceiling needed to be an air barrier, insulation, and also on top of that, a 2-hour fire rating. So the least bad assembly that we came up with was, existing floor, closed cell spray foam in between the rafters, and then run a continuous layer of zip R sheathing, taped joints sealed at the perimeter, something that's eminently inspectable for this type for penetrations, and then run all the services below that in a furred cavity below the double layer of rock. Another issue that we dealt with was thermal bridging at the windows. So we sent the preliminary plans into FIAS. They provided some feedback saying, hey, you got some thermal bridging, possible condensation risks. Like, yep, that's fair enough. The masonry is left exposed there. The limiting factor is that all of the window dimensions are strictly constrained by the historic requirements of this project. So there's not much wiggle room to work with. So in some cases, we could add like a block of EPS foam to basically provide insulation, air control, condensation control. But in other cases where we only had so much space to work with, and that's about all we could do. Another tricky component was the whole air control, air barrier part of things. So this shows the layer cake of what we're dealing with: the vented attic up top, exterior, 2 floors of residential in the retrofitted building, unconditioned parking garage below, and a heated commercial space. So one problem was the storefront, historic single glazed aluminum storefront had to be retained by historic. So we built a new storefront in board of that. But one of the problems is that even though the commercial space is heated, it's excluded from the passive house boundary. And unfortunately, it is included as this boundary is part of the blower door test. We're not allowed to do a guarded test. Something I don't agree with, even though both of these spaces are running at the same temperature. That's going to be something that'll need to be resolved during construction. Just to wrap this up, in case folks were curious about the new construction assemblies for that infill building, most of it is pretty straightforward. The roof is completely generic. The wall is kind of interesting, as well as the deck over the parking garage. So that shows their wall assembly. We have 2x6 stud frame wall, cellulose insulation. Like I said, we're trying to go with carbon storing, low carbon materials in this project. Air and water control layer, 4 inches of mineral fiber on the outside, and our furring and cladding system. On the deck over the parking structure, it is a corrugated pan deck. One way to do it is to insulate on the underside, but of course there's all this structure to deal with. You have a massive amount of thermal bridging that you need to wrap. It turned out to be logistically easier. Let's just build a raft of 6 inches of EPS on top of the slab, thermal breaks where we have structural interior walls, and a gypcrete layer on top of that. Nice continuous sheet of insulation running across the entire assembly. Okay, and that was my part of the talk.